Welcome to part 2 of the wing sizing video using the analytical method from the Ultralight Airplane workshop. If you have not seen the part 1 of this video yet, I'll put a link up in the upper right hand corner of the screen. It has been a couple of months since we did part 1, and in part 1 we really didn't have a good choice on what to use for the coefficient of lift for the wing. So what we ended up using was the coefficient of lift of 2.0 that we obtained using the FAA's approved method from Appendix 2 of Part 103-7. Recently, we finished selecting an airfoil for the UWS-1, and now that we have that airfoil, and we've decided to use full-length slotted flaps for the wing, we can figure out what the maximum lift coefficient will be using those slotted flaps and that airfoil, and now we can work backwards to figure out what our surface area for the wing can be. So let's get started. Let's review what we came up with from part 1 of the wing size video. The result was a surface area of 108 square feet. We were estimating a span of 30 feet, which really wasn't part of our area calculation, but we were coming up with 30 feet as a reasonable compromise between a minimum span of 24 feet for stability and a maximum span of 37 feet to fit in our 16-foot trailer. We also expected the span of our flaps to be more than 50% of the span of our wing, and that's because of Appendix 2 of the FAA Advisory Circular 103-7. And using that appendix, we came up with the coefficient of lift for our wing of 2.0. And of course, we fed into the equation to come up with 108 square feet, a weight of 424 pounds, at a stall of 24 knots. So we have a starting coefficient of lift for the wing. Let's figure out what the section coefficient of lift will be. And we're still basing this on what we came up with on part 1 of our video. Now, using from information we got from Barnaby Wainfan on his airfoil selection series, Part 8, we can assume an efficiency of our wing, a lift efficiency, which is different than drag efficiency, of at least 85% at stall. That means we can use a conversion from our wing lift coefficient to our section lift coefficient. So we start with a wing lift coefficient of 2.0. To get our section lift coefficient, we take our 2.0 divided by 0.8, which is 85%, and we come up with a section coefficient of lift of 2.35. And we know from the Horner book, Fluid Dynamic Lift, that with plain flaps that are 20% of the chord, we can get a section coefficient of around 2.3. Well, that means we would have to have pretty much full span flaps to reach our wing coefficient of 2.0. If we were to increase the chord of our flaps closer to 25% chord of the wing, then we can get that section coefficient up closer to 2.4. If we were to do that, we could then possibly set the span of the flaps closer to 75% of the span of the wing, and probably still come pretty close to reaching our 2.35 section coefficient, and thus reaching a 2.0 wing coefficient of lift. Now, it's not a bad solution. We could actually go with that and have our wing size designed so the wing size would stay about the same. It's just that the flaps would now be designed and ready to go, and we would have plain ailerons. But what's the fun in that? Let's see what we can do with different styles of flaps. In the previous calculations, we were assuming plain flaps, and I'm going to assume you kind of have an idea what plain flaps are. But now let's think about flaps that give us a little more lift. And in this case, we're going to talk about slotted flaps. Over here on the left, you can see what a slotted flap looks like when it's in the neutral position. So it's not actually adding any extra lift. Down here, you can see 2 examples of the movement of a slotted flap. Now, in this case, these are using just a simple hinge. You won't get quite as high a coefficient of lift if you move your slotted flap using a simple hinge as you would with a more complex hinge, where the nose and the trailing edge don't move in the same arc. The nose would move differently than the trailing edge. But as you can see, what happens in this 10% flap deflected, the trailing edge will drop down and back, and the nose will move nearly straight back. But then what happens is a gap is created here between the nose of the flap and the wing. This gap is going to be wider here at the bottom of the wing where we have higher air pressure, and it's going to be narrower up here at the trailing edge of the wing, which will cause the air to accelerate and shoot through this gap nearly tangent to the surface of the flap. That accelerated air re-energizes this boundary layer and helps prevent it from separating. This effectively gives our wing much greater camber, so this increases the lift of the wing without significantly increasing the drag, at least compared to plane flaps. Think a little bit about how plane flaps work. You've got a semicircle up here where the nose of your flap is, and that nose stays in the same position, at least around the hinge line right here, and then the trailing edge flops down. So what you're going to have then is a fairly abrupt change in this surface area here when you start dropping this trailing edge down, and you're going to get separation and thus a significant amount of drag, particularly as you increase the angle of deflection. And in addition, if you have unsealed flaps, you have an even worse situation. You've got a gap here between the wing and the leading edge, and instead of the air shooting out right along the surface of the flap, it actually shoots almost straight out. That's even worse because it further disrupts this boundary layer and increases the drag even more because your boundary layer is separating even worse. So the slotted flap has a potential for significantly less drag for increased lift compared to the plane flap. Now back to the slotted flap. As we rotate the flap back around this hinge point, we are effectively increasing camber more and more. But that also increases this gap more and more. And we get to a point where this gap gets so large that it starts to resemble the gap of a plane flap, where the air is not moving as much tangential to the surface of the flap and is more shooting out away from the flap. And that's when we start getting separation and start increasing the drag. This is another hinge point for the same kind of flap, and you can see that by moving the hinge point further down, this trailing edge moves back farther and farther. So initially we actually get an increase in lift over the same deflection for this one, because what we end up doing is effectively increasing the chord of the wing, so increasing the surface area of the wing, and that will give us more lift at these lower deflection angles. But as the deflection gets greater and greater, this gap gets larger and larger and becomes less effective. Well, how much lift can we get out of this? With a slotted flap with a simple hinge, we can get somewhere between 2.5 to 2.6 for maximum coefficient lift. It's closer to 2.5 if we use a simple hinge. If we use a more complex hinge mechanism, we get closer to 2.6. And of course, you can get that information from Horner. If we utilized a full span slotted flaps, what would our wing coefficient of lift be? Because this was a section coefficient lift up here. So if we take our section coefficient of 2.5 and multiply by our 85%, we end up with a wing coefficient lift of around 2.13. And that compares with 2.0 previously. So we could get a greater coefficient lift with these slotted flaps for our wing. Let's get into a couple of the other advantages and disadvantages of these slotted flaps, at least compared to plane flaps. One possible advantage is that if you do a good job of fabricating your slotted flap and your wing, you can actually seal this slot in here so you don't have air traveling from the high pressure underneath to the low pressure up above. So at normal cruise then, we should not have any air flowing through here, causing a disruption of our boundary layer and thus increasing drag. So that's another potential advantage of the slotted flap, as long as we do a good job of fabrication. But we also have a disadvantage, and that's because of having to hinge the slotted flap far below where our wing is. With the plain flap, our hinge is built inside the wing. But with the slotted flap, our hinge has to be down below. An alternative is a slot mechanism, and you can have one slot or two slots. If you're doing two slots, you'd have one of those slots be to position the nose as you're sliding the flap back. The other slot would be to position the trailing edge of the flap as you're sliding it back. For something trying to represent a hinge, you could probably use one slot for both. But the difficulty with that is that that slot's going to end up hanging down here into the airstream. Even if you only want to try to manage a short slot, it's going to hang down a little bit. And if you're going to go to the trouble of creating a slot that's going to hang down like this, you might as well skip trying to emulate the hinge and go with the more efficient slot path, which in this case is kind of interesting. The nose would move down and then back and then start to move up as it comes farther and farther back. So it's fairly complicated, whereas the trailing edge can move almost in an arc, just like with the hinge. So if we don't have this slot mechanism for the slotted flap to slide along, we have to have something that sticks down below the wing that'll hold the hinge that the flap will then rotate about. So that's going to be something like a little pylon or a flat piece of metal that sticks down. Something will have to stick down from the wing and stick down from the flap. Now on the UWS-1, we're going to take advantage of a couple things. We will have one hinge built into the side of the fuselage. Having this hinge built in the fuselage, then we will not have to have something sticking down from the wing. As far as the flap goes, we can fare the portion between the flap and the hinge into a recess in the fuselage so that at least in cruise there's no drag. Another thing that we can take advantage of is we plan to have the engines attached underside the wings on some nacelles. What we can do is make sure those nacelles drop down far enough that we can use the side of the nacelle for our hinge. So once again, we don't have to have anything dropping down from the wing. The nacelle will replace that, and we can fare, just like against the fuselage, we can fare the connector between the hinge and the slotted flap into the side of the nacelle. So at least at cruise, we don't have drag. So that leaves some mid-span hinges and a hinge out at the wingtip if we're going with full-span slotted flaps. Well, what we can do, at least out at the wingtip, is let's take advantage of having drooped tips. Tips that droop down far enough that we can attach a hinge to. Also has the advantage of having that drooped tip be dual purpose. It can be a hinge, plus it can be like a winglet, which will increase our effective aspect ratio, which of course helps with the efficiency of our wing. So then the only drawback then is mid-span. Let's say between the engine nacelle and the wingtip, we'll have at least one, maybe two places we'll need to support this flap when it's deployed. Otherwise it's liable to bend and twist more than we want. And in that case, I'm toying with the idea of going ahead and sticking a simple slot up in here that with a roller in just the nose. And that would be buried within the wing so it does not have to stick down in the airstream. So we'll probably have a little something that sticks off the front of this nose, and we'll have a curved slot with a roller for that extension on the nose to roll in. That will at least give support here at the nose. It would not support the trailing edge. So what we may have to do then is just design the flap to be stiff enough so that the trailing edge will not bow out. That's something we'll have to do a little bit of analysis on. Now that we've come up with a coefficient of lift for wing that's using full span slotted flaps, we can figure out a new surface area for the wing. Now remember, the coefficient of lift for the wing previously was 2.0. Now it was with full span plane flaps and from part 1 of our wing size video. And the wing size that went with that coefficient of lift of 2 was 108 square feet. So let's calculate the new size of our wing. Now using the old wing size and old coefficient of lift, we can divide by the new coefficient of lift for the wing, and we get 102 square feet. So we saved roughly 6 square feet of wing area, so we can make our wing area smaller. Let's just assume that our 108 square foot wing weighed about 90 pounds, and this is just an educated guess from some previous wings that I've weighed. What would be our weight savings then if we change the surface area from 108 square feet to 102 square feet? The way we would do that is we'd take our 90 pounds and we would then divide our 102 by 108 and subtract that from 1. This basically gives us our percentage. Then the result of this calculation would be 5.4 pounds that we would save. Now, unfortunately, it's not really that simple. That's really only considering reducing the size of the wing when changing the coefficient of lift. It's not really taking into account some of the more practical matters. For example, to get that better coefficient of lift for the wing, we changed to a slotted flap using a long hinge hanging underneath the wing. Well, that long hinge is going to have extra hardware to connect it to the wing and to connect it to the flap, and that would add weight. So I'm guessing that probably in the long run it would just even out. The extra hinge material would probably end up being around 5-6 pounds, so the weight savings will probably even out. Now, another advantage we get by reducing the size of the wing is that the moment created by the wing will be smaller, because if you remember from an aero terminology video that we made over coefficient of moment, the moment is directly related to the size of the wing. So the smaller the size, the smaller moment. Well, having a smaller moment then means that we can make our horizontal tail size smaller, and that will save some weight too. As I was doing my research on slotted flaps, I ran across this very interesting NACA report, and the report is 3I20. This is back in the early 40s, about an interesting double slotted flap. Now, most of the double slotted flaps that I had seen had a very complicated deployment mechanism, but this one was actually very simple. In this case, the leading part of the airfoil of the flap and the trailing part are fixed in relationship to each other. They do not move independently. And when you're deploying the flap, you rotate it, at least when you're deploying from 0 degrees to 45 degrees, around a pivot point. You don't have a complicated movement path for the nose of the flap. This one did have a potentially slightly more complicated movement, in that if you wanted to deploy from 45 to 65 degrees, you then rotated about a different hinge point. But I don't think it's necessary, and we'll talk about that. When it's in the non-deployed state, when you're in cruise, it is completely stowed inside a cavity in the airfoil. And so there should be a very low drag condition for the airfoil. These slots behave in the same way that we talked about for the single slotted flap. When the flap is deployed, in the trailing slot, you have a large opening in the high pressure side of the flap. The air is going to flow into the slot, accelerate, and come out tangent to the top of the flap. This should help keep the boundary layer from separating and keep it energized. Now on the leading slot, same thing happens. It doesn't look quite as aerodynamic, but you have air entering this very large opening, and the slot gets accelerated and again comes out tangent to the top of the leading airfoil of the flap. This should keep the boundary layer of the airfoil attached to a very significant angle of the flap deployment. Now let's talk a little bit about what the study found. You can get up to 3.4 lift coefficient when it's deployed to 65 degrees. But even if you only go up to 45 degrees, and that's just using the single hinge pivot point, you can still get up to 3.2. That's pretty darn good. Now keep in mind that this is at a rental number of 6 million. Now we're down around 1.7 million. And that should drop the coefficient of lift around 0.1, so we should be able to get at least 3.1 at our Reynolds number for the UWS-1. Let's find out what the surface area of our wing would be if we just change the coefficient of lift for this double slotted flap. Let's be a little bit conservative. Instead of 3.1, let's assume we'll only get up to 3 on our coefficient of lift, or max coefficient of lift. And that would be at the 45 degree deployment angle of the flaps. Now let's recalculate our surface area then. Starting with the original one of 108.5 feet with a coefficient of lift of 2, then we divide by our section coefficient of lift of 3.0 multiplied by our 85% efficiency of the wing. That ends up giving us 85 square feet for the wing. We dropped from 108 square feet to 85 square feet. Well, that's pretty significant. Well, that's going to change the angle of attack of our wing when we're cruising a little bit. It's actually going to have to increase it. We're going to end up increasing the wing loading of our wing, because we still have the same load, 424 pounds. Let's recalculate that. If you remember, we're going to figure out our coefficient of lift at cruise by taking the weight, dividing it by Q, which is our dynamic pressure, multiplied by the surface area of the wing. You may not remember, but we calculated Q back in Part 1 to be 10.2 pounds per square foot when we're cruising at 55 knots, which is our maximum allowed cruise speed for a Part 103 Ultralight. So let's go through that calculation. We stick in our numbers and we come out with a lift coefficient at cruise of 0.49. Well, it used to be 0.38 with our original wing. That actually is a very nice result, because you may remember in our airfoil selection video, we were having a hard time getting an airfoil that would have low drag down to our lift coefficient of 0.38. Well, if we increase it 0.49, now it's much easier, because most of them did have fairly low drag up around the 0.5 area. So that's a great thing for us. What should we do next on figuring out the wing size, and what do we do following that? I'm going to hold off on the final selection for the flaps, and thus the final selection for the wing size, until I can do a little bit of a comparison on the moment arms that will be generated by various possible configurations. The ones we talked about in this video are flaps that only cover 75% of the span with a plain aileron with the other 25%, or having flaps that run the full span of the wing. Of course, in order to do that, we're going to have to do something about our ailerons. And I do have a potential aileron selected if we do full span flaps, and I will do a separate video on that. But first, we're going to have to do a little bit of moment arm comparisons. Once I've done the moment arm comparisons, I'll probably then select the flaps and then fix the wing size. Well, I hope you enjoyed this video. We have a whole lot of more design videos coming up, and we have some more work in the shop. We'll do a little more vacuum infusion. I'm also going to make a video on vacuum bagging a wet layup, and we're going to try a new vacuum infusion resin. Another thing that's coming up in the works before too long is we're going to start tearing apart some carbon fiber. I'm working on a fixture to hold some carbon fiber to rip it apart and shear. We will test some of the carbon fiber samples that we've created so far. So look forward to that.